Alright, in this video we will be looking at problem 10 from chapter 13, which you can find on page 383 of the book. This problem states that Miranda, a satellite of Uranus, can be modeled as a sphere of radius 242 kilometers and mass 6.68 times 10 to the 19th kilograms. As George said, has probably already told you 1,000 times, the first part of every problem is to draw a picture, which I have so neatly drawn here. In this, I have labeled capital M, lowercase p, to be the mass of the planet, and capital R to be the radius of the planet. Part A of this problem asks us to find the acceleration of the free fall acceleration on its surface. To solve for this, we will use Newton's law of universal gravitation, and from this equation we can solve for the gravitational acceleration on this planet, which is given by the equation lowercase g, which is the gravitational acceleration on the planet, equals uppercase G, which is Newton's universal gravitational constant times the mass of the planet over the radius of the planet squared. Substituting in our values, we get 6.67 times 10 to the negative 11 times Newton times meter squared, which is Newton's universal gravitational constant, times the mass of the planet, which is what we were given, all over the radius squared. Solving this, we get 0.0761 meters over seconds squared. The next part of this problem asks us, or states, rather, a cliff on Miranda is 5.00 kilometers high. A devotee of extreme sports runs horizontally off the top of the cliff at 8.50 meters per second. Velocity, for what time interval is he in flight? Again, the first part of this problem is to draw a picture. In this problem, I have drawn a picture like this, where this is my sports guy, this is the initial velocity in the x direction that he's running, this is the height of the cliff, this is the radius of the planet, and this is my coordinate system, where in the downward direction it will be negative, and the upward direction is positive. You can see that. Alright, in this problem we will ignore the difference of about 4% in the gravitational acceleration between the lip and the base of the cliff. To solve for the time in this problem, we use the kinematic equation that states that the y position, the final y position, equals the initial y position plus the initial velocity in the y direction times time plus 1/2 the acceleration in the y direction times t squared, which is time. This drops out immediately because there is no initial velocity in the y direction because it's a free fall problem. I set this as I called the top of the cliff my initial position. I stated that the bottom of the cliff is my final position. So substituting in those values, we get something like this, where 0, which is the final position on the bottom of the cliff, equals 5,000 meters plus 1/2 times negative 0.0761, the negative being from the coordinate system I chose, times t squared. Solving for t, we get t equals the square root of 2 times 5,000 meters all over 0.076 meters over second squared, which equals 363 seconds, which is the time interval our guy is in flight. Part C of this problem asks how far from the base of the vertical cliff does he strike the icy surface of Miranda. To solve for this part, we will also use the kinematic equation similar to that we just used, but now we will use it for the x direction, which gives us the final position in the x direction equals the initial position in the x direction plus the initial velocity in the x direction times t plus 1/2 the acceleration in the x direction times t squared. This value, our initial position in the x, will be equal to 0. Our initial velocity in the x direction is equal to 8.5, which is already given, and our last term here will go to, initially we'll drop out because there was, obviously there's no acceleration in the x direction. So then we'll get an equation like this, where 8.50 velocity times 363 seconds equals 3.08 times 10 to the third meters, which will be our answer for part C. Finally, part D of this problem asks, what is the vector impact velocity? To solve for the vector impact velocity, we will have to solve for both the magnitude of the velocity when the sports guy hits the surface of the planet and the direction of the velocity of the vector of the velocity vector when it's when he hits the surface. So first, I will solve for the magnitude. We can solve for the magnitude of the velocity by taking the velocity in the x direction squared plus the velocity in the y direction squared, and all of that square rooted. To do this, we must find our velocity in the y direction. To find our velocity in the y direction, we will use the kinematic equation. The v final equals v initial y plus acceleration in the y direction times t. Substituting in our values, we get negative 0.076 times 363. This will give us a velocity in the y direction, a final velocity in the y direction of negative 27.6 meters over second. Now, substituting this in to our equation will give us this value, and solving this equation will give us 28.9 meters over seconds for our magnitude of our vector. Now, solving for the direction, our direction will equal our angle, which will equal the arctangent of our velocity in the y direction over our velocity in the x direction, which is equal to negative 27.6 over 8.5. This will equal 72.9 degrees below the x-axis. So our answer to part D will be the vector, the final velocity vector will be equal to 28.9 meters per second at 72.9 degrees below the horizontal.